Welcome to the Geomechanics simulation webinar with Irazu and Coreform Cubit. So I'm your host again, Matt Cederberg, here with Omid Mahabadi from Geomechanica. So in today's webinar, you will be introduced to the leading rock mechanics simulation software Irazu, as well as to Coreform Cubit, which is a mesher and preprocessor that's widely compatible with simulation codes in many industries, including the Irazu software that we'll be focusing on today. So today's webinar is part of our webinar series showing how Coreform Cubit can be used to prepare and mesh geometry across industries. Again, today's webinar is focused on geomechanics. Our next webinar coming up is August 20th, focused on Coreform Cubit basics. You can register for that and watch all of our recorded webinars at coreform.com. So as a reminder, today's webinar is being recorded. During the webinar, you can use the Q&A or the chat session to ask us questions. We'll either type them back or ask Omid when appropriate. We'll have a Q&A at the end. And finally, at the end of the webinar, we have a one-question post-webinar survey, and we'd appreciate it if you, that will pop up in your web browser. If you could answer that, we'd appreciate it. So the learning objectives of today's webinar are, one, to help us all understand the unique challenges of geomechanics simulations, to learn how Irazu can be used to solve rock mechanics problems, and then finally learn how Coreform Cubit can be used to clean up and mesh data for Irazu simulations. So I'll go ahead and introduce Omid. Before I do that, we have just a couple of polls so that Omid can get a better sense of who his audience is today again. So let me launch the first poll. Let's see. I think these are all coming up at the same time. So we just have some questions as far as your familiarity with what we will be talking about today. If you've used the Irazu software, if you've never used it, tried it, you've used it regularly. If you've used Coreform Cubit at all, or if you use it regularly. And then also, the Irazu software can be used across many sub-industries in geomechanics. So if you are able to be more specific as far as what specifically your industry is, that's also just interesting and helpful as Omid speaks to us today. So I'll go ahead and leave this open just for another 5 seconds or so. Okay. So we'll go ahead and share the results with everyone. So as far as Irazu, we have some regulars, a number of people that have never used it before. So hopefully this is a great introduction. Is similar with Cubit. We've got a number of people, the majority have never used Cubit before, some regulars. So this will be hopefully a good introduction to Cubit for you. And then predominantly civil engineering. So great, thanks for those insights. All right, so now to introduce Omid. Dr. Omid Mahabadi is the president, CEO, and a co-founder of Geomechanica. He holds a PhD in rock mechanics and civil engineering from the University of Toronto. He specializes in development and application of advanced numerical simulation tools to solve rock engineering problems in civil, mining, and petroleum engineering. So with that, go ahead, Omid, thank you.
All right, thanks, Matt, for that introduction. Hello and welcome, everyone. Thanks for joining us today. As Matt kindly introduced me, I'm the CEO and president of Geomechanica. I'm going to share my screen right now. Just give me 1 second. Since a lot of you may not know who we are, I will very briefly introduce who we are, and then dive into our quick introduction to our Irazu software, and then eventually I will show some case studies and live demos of Cubit and Irazu. So for those of you who don't know who we are, Geomechanica is a company out of Toronto in Canada. Our mission is to solve challenging rock mechanics problems through the development and application of state-of-the-art numerical simulation methods. And at the heart of that is the Irazu geomechanical simulation software, which helps us solve complex rock mechanics problems through cutting-edge high-performance computer simulations. Irazu could be applied in a wide range of domains, including civil engineering, mining, petroleum, geothermal, as well as research and development. Using Irazu, we provide computational geomechanics consulting, so customize simulations and analysis using Irazu in the same domains that Irazu could be applied in. And finally, we have a rock mechanics laboratory testing facility here in Ontario, where we serve the civil and mining industries, mostly locally. So what was the motivation behind developing Irazu? The motivation was obviously some of the common limitations of conventional simulation software. And really, I'm not going to go into a lot of details on this, but most conventional software that are used in modeling rock mechanics, especially fracturing in rock mechanics, don't have very strong bridge of fracturing and progressive damage formulations. They typically oversimplify the rock mass structure. For example, you typically can include a limited number of joints and faults. Most of the conventional, finite element, finite difference software, simulation software are restricted to small displacements and rotations, and even with plasticity and more complex constitutive models, you can only capture large strains, but not necessarily large displacements. And in many cases, risk analysis is limited to understanding the hazard only. So you would know if structure is going to be stable or not, but you won't know what happens if there is any sort of instabilities in the structure. So with those motivations, we developed Irazu, which is a versatile 2D, 3D finite discrete element package for the analysis of large deformations, fracturing, stability, and coupled processes in rock masses. The integration of various multi-physics solvers and advanced features into a single software package enables Irazu to be used for a very wide range of geoengineering applications, including underground excavations, slope stability, tunneling, dynamic analysis, mining, geothermal, and reservoir geomechanics. So if I wanted to give you a very brief overview of Irazu and kind of isolate three main features, these will be these three. So first is high performance computing thanks to GPU computing, and the ease of use using our intuitive user interface, which gives you open access to both inputs and outputs of the simulation. In addition to that, we have multi-physics solvers that allow you to simulate coupled fracturing, mechanical, hydraulic, and thermal processes while including realistic rock mass representation. And finally, thanks to the FEM plus the DEM formulation, Irazu is a single software package for all your geomechanical simulation needs. So you don't really need to go and have 3 or 4 different software packages for specific applications. As I mentioned, Irazu is equipped with multi-physics simulation solvers that allow you to flexibly couple all of these 4 major solvers using two-way coupling. So the coupling, the solvers could communicate back and forth with each other. The 4 solvers are mechanical, hydraulic, transport, and thermal. So using the mechanical solver, you can model rock deformation and fracturing, contact detection and interaction of discrete bodies. So you could go from a fully continuous medium to a fully discontinuous medium, or start with discontinuous medium and capture the interaction of these discrete bodies. Using the hydraulic solver, you can model fluid flow through fractures, fluid injection, fracture flow, and growth. And the transport solver is specifically designed for hydraulic fracturing applications, so for proppant emplacement and transport, as well as proppant sealing. Finally, using the thermal solver, you could model thermal flow, thermal stresses, and fracturing. So, as I said, this is a very, brief introductory webinar to Irazu and Cubit. So I will just give you now two case studies. So the first one is the performance analysis of an open pit mine wall. So on the right-hand side, you see a CAD drawing of the open pit. This is a large open pit mine that was undergoing significant wall deformations and instabilities, especially in this area where my cursor is. The system behavior was very complex and characterized by an interplay of major discontinuity surfaces, including faults and foliation, as well as groundwater flow. Our first task was to back analyze to understand the deformation and failure mechanisms of the open pit that were observed in the past, and to calibrate the models for subsequent forward analysis of future cutbacks or pushbacks. In this case, this mine has been operational for quite a few decades, and the client was working with major consultants that were using conventional tools, but these conventional tools or conventional software failed to correctly capture the main processes involved, as they required numerous simplifying assumptions. So they were not really able to understand what was going on with those software. The solvers were not converging. So that's why they came to us to see how we could help them. So what was our solution? It was using Irazu, which is well suited to analyze the mechanical behavior of rock slopes and can capture a wide spectrum of slope behaviors without the need for complex constitutive models. So the spectrum of behaviors that we could capture include continuum deformations, fracturing, complex failure kinematics, and large displacements. We incorporated a large number of faults and other discontinuity surfaces in the model. You see a screenshot of the mesh with all the fault surfaces that were included in the 3D tetrahedral mesh on the right-hand side. This, this is the example that I'm actually going to show to you later on. Just have this example in mind for the actual Cubit demo. In addition, we incorporated groundwater pore pressure effects or effective stresses together with a coupled flow of water through rock fractures. So this was really a hydromechanically coupled model. So we managed to successfully back analyze the wall deformations of the current cutback with realistic deformations and acceleration patterns. We validated these against quite a bit of field data, including prism measurements, extensometer data, radar readings, and so on. And the deformations, where we see the deformations, these all match the field measurements really well. We were able to quantify the effect of pore pressure on the slope performance and confirmed that groundwater flow through the faults could create large deformations on the slope. So it wasn't really groundwater flow in the slope itself, but it was in a few faults that were connected to the groundwater source. We then predicted the performance of future cutbacks under different geomechanical scenarios, including excess pore pressure, and provided ranges of expected slope wall deformations. And finally, we suggested remediation strategies such as dewatering campaigns to further stabilize the slope, thus cutting costs and increasing mine safety. The second and last case study is the geomechanical analysis of hydraulic stimulation in unconventional reservoirs. So what is the challenge in hydraulic stimulation? Hydraulic fracturing design generally is addressed with simplistic models that is generally tempered by local experience, so a lot of history matching and so on. The interactions between injecting and existing fluids in situ and induced rock mass stresses, newly created fractures, and natural discontinuities is generally neglected. The reservoir performance in response to changes in geomechanical conditions is generally ignored or not, predicted well. And there are treatment and recovery inefficiencies, loss of wells, and lower return on investment. So what is the solution? Again, using Irazu, which is equipped with with novel modeling capabilities for the stimulation and production of unconventional reservoirs. Irazu is fully coupled using the hydromechanical solvers as well as a transport solver. You could, incorporate discontinuity surfaces and heterogeneities. And, our fracture model accounts for tensile, shear, and mixed mode failure modes, which is something that many conventional software packages used for modeling hydraulic stimulation ignore. Most of them assume fracturing only in mode 1 or tensile. Finally, Irazu enables accurate computation of stresses, strains, and fracture without minimal simplifying assumptions regarding fracture shape or growth trajectory. You don't really dictate where the fractures go, in which direction, and what's the shape of those fractures. So using Irazu, you could optimize hydrocarbon extraction by numerically experimenting with injection rates, wellbore spacing, and fluid properties. Could also reduce drilling and production costs by predicting and optimizing the stimulation process. The myth in the industry is just, inject more, fraction more, but that's really a myth. You could also evaluate the effectiveness of new stimulation methodologies and techniques, including the analysis of completion strategy, well spacing, and stress shadow effects. And finally, you could increase safety by assessing hazards such as caprock integrity, wellbore damage, induced seismicity, and groundwater contamination. On the right-hand side, you're seeing an animation of a 3-stage injection, and that is also tapping into natural discontinuities. And this simulation is capturing stress shadow effects and the effect of multiple injections in the same cluster. So, what are the competitive advantages of Irazu? Irazu is an all-in-one general-purpose simulation tool for the design and analysis of a very wide range of geoengineering applications. And compare this with having to maintain and purchase multiple tools for specific applications. So rather than having to purchase, maintain, and train your staff on using 3-4 different software packages, you just use Irazu. Irazu is also developed by a new generation of experts that are actively pushing the boundaries of commercial geomechanics simulation tools. And finally, the software is based on cutting-edge research and development in both geomechanics and high-performance computing. We were probably among the first engineering software firms globally that started using GPUs or graphics cards for doing actual computations. So with that, now let's focus shift our focus to more specifically towards geometry and meshing. There are certain challenges for manipulating and cleaning the geometry and meshing, specifically in our field, which is geomechanics, rock mechanics, or geoengineering. So what are some of the specific meshing challenges in geoengineering? Obviously, the quality of simulation results relies heavily on the mesh quality. There is sensitivity of fracturing results to mesh sizing and orientation. So if, for example, you use a structured grid, then that's where the fractures are going to grow, and that would result in unrealistic results. Also, mesh quality dictates the value of time step size that is used in the explicit time integration scheme of Irazu, and as a result, it affects the computational performance. So if you have a few very tiny elements or poorly shaped elements, those will decrease your time step size, then increase the simulation time. In addition to that, rock material is generally characterized by the presence of defects, cracks, faults, and other discontinuities that often need to be explicitly included in the mesh. So you need a meshing tool that could very easily incorporate discontinuities as well as heterogeneities. Dealing with natural systems where domain shapes are completely irregular is also another challenge. Um, let's say in manufacturing, aerospace, and so on, your domain is man-made. So, you have perfect shapes, cylinders, hexes, and so on. When you're dealing with natural systems, you really don't have a nice shape. So that kind of complicates, surface or volume definitions usually. Mesh sizes also need to change throughout the model to use smaller elements in the areas of interest where you expect to see deformations, fracturing, fluid flow, and so on. And then you use larger elements as you go closer to model boundaries, because you have to move away from the area of interest so that you don't have boundary artifacts changing your results. Finally, you need a powerful and flexible meshing tool that allows you to clean up and prepare the geometry for meshing, and could also produce high quality meshes. And this is where Coreform Cubit comes into the picture. So what would be a typical Cubit workflow for Irazu meshing? Generally, as I said, your geometry is coming from natural systems, so you might have some sort of a geological modeling software or other CAD software where you have your domain geometry. So you would start by importing the model geometry, typically in some sort of a CAD formats, such as ACES, IGES, and so on. You then have to carefully inspect the geometry for defects, small features, and meshability, because often the geometries that you import from CAD will have tolerance issues, or there might be duplicated lines, surfaces, and volumes. So you have to fix these issues with the geometry, and generally you have to merge and imprint to get conformal meshes. Then you would set the element sizes on lower level entities, such as curves and surfaces, so that you have a good control on mesh sizing. You then set the meshing schemes, then you mesh and smooth the surfaces and volumes. Obviously, you have to then check for mesh quality and fix any possible issues. There might have been some small features that were created due to merge and imprint. So you kind of go back, and iteratively fix some issues, mesh, and check the quality of that mesh. Finally, when you're happy, you add elements to blocks and nodes to node sets for easier material and boundary condition assignments in Irazu. So rather than having to manually select elements and nodes in Irazu, you just select sets. So sets of, or groups of elements and groups of nodes. And once you're happy with everything, you export the mesh in IMP format. That I would now like to give you a full software demo, actually, of I'll start with Cubit and go from there. So this is not really going to be a Cubit tutorial because that will be really out of the scope of this webinar today. So I'll try to just walk you through my process and the steps that I just outlined in terms of the Cubit workflow for Irazu. So if you've used Cubit before, you're probably quite familiar with the interface. But if you haven't, this is where you would see, after you import stuff, you would see, your geometries on the right-hand side. You have controls in terms of, creating and modifying the geometric entities such as surfaces, volumes, and so on. And you mesh. When you start using Cubit, you would probably use, the command panel quite a lot. So, you would click on stuff and see what happens. But as you start doing that, you would realize that whatever command or whatever action you take on the right-hand side, you will see it printed at the bottom, and you could also see it in the history. And this is really very powerful because it allows you to, just copy and paste from here into a text file that you see on the left-hand side, which in Cubit lingo is called a journal file. And with that, you could really do a lot of things very quickly. So it's very similar to recording a macro. So my workflow is that I generally start, clicking here and there. Then I start to record these into a journal file, and then I will play that journal file. So that way, if I have to do things, iteratively, and I have to do it for a couple of times, I don't have to click, 100 times and, change, because every time you have to click, you have to, go from different menus and, select different stuff. So that is usually how I would do it. I'll start doing things graphically, then I head to the history tab here at the bottom on the command line, or, you could also do it here, but here there's some other prints and, communication with the user. Then I will paste it here, and then I will, play the macro or the journal file. You could play the whole thing, or you could, if you're just playing with certain areas, let's say you don't want to smooth or look at the quality, you can just select the sections you want to play, right click and play selected. So again, in this example, I want to go back here. So this is the problem that I'm going to show you. As you notice here, I have faults here. These faults were coming from the geological model that the client provided to us in CAD format. I had to clean them in CAD software initially because these were, very poorly shaped surfaces. So after cleaning those up, I exported them into an IGS file, which I could then import into Cubit. So let's just do that. Okay, so you see I played that and I'm imprinted. So these are all the fault surfaces that I had cleaned a little bit in a CAD software. Okay, so once I have these, I will imprint and merge it, and I will mesh all of these. And so let's just play the whole thing. So import, now it's importing, and as you notice at the bottom, the commands are getting called sequentially. So what I've done here is that I've set the mesh size to be 25 here, 25 meters. I use a Tri-Delany meshing scheme. I mesh the whole thing, I smooth it, and then I check for the mesh quality. And as you notice, the quality is pretty decent, because your quality matrix or the shape matrix in this case is above 0.6, which is pretty good for triangles. Usually the areas where you see issues are where you have intersections between different surfaces. And obviously the first time you import your CAD file, you're going to see some issues. Then you can either, try to clean up in Cubit or go back to the CAD software, clean it up there. So this initial step is a little iterative, but within a couple of hours, you should have a working surface mesh of your faults. The next step is to bring in the actual slope volumes and slope geometry. So typically I have different journal files. So let's say I run this. Once I'm happy with it, I'm happy with the mesh, I go ahead and save it. So you could save it as either a Cubit file. So usually that's how I do it, or in the old versions as a trellis file. So once you're done with that, now you would focus on the actual surface or slope geometry. So let's just go ahead and play this. So you see this is the slope geometry that I have for my problem again here. Let me just show it to you. So this is the slope geometry for a section of this open pit slope. So the way I went about this is that I fit a surface on the slope here onto the main features, such as the ramps and benches and so on. Then I divided my volume into two sections. So the volume inside, this volume that I just selected, this is what I call the fine volume, where I will use a smaller mesh size. and then the volume around it is where I will gradually increase the mesh size to the model boundaries so that I don't have too many elements. So in this case, once I mesh the whole thing, I'll end up with about 250,000 elements. If I don't do that graded meshing and increase mesh sizes towards the model boundaries, I'll end up with 2 million elements. So that will be at least 10 times more runtime. So anyways, in this case, I'm not going to mesh this geometry here yet. So let's just run this whole script again. So what I'm doing, I'll just importing the two volumes here, and I'm merging everything so that I will end up with conformal meshes. So there won't be any discontinuities in the mesh on the boundaries between the two volumes. Okay. So once I'm happy with this, I'll save this as another Qubit file, and then I go to my main journal file where I glue everything together. So the first order of business here was to import the slope geometry here. Then, as I said, what I do is that, so let's just do that. So I play this section here. So in this case, as you notice, I brought in the two slope volumes here, right? The fine area and the coarse area. And I just set the mesh sizes on some of the curves. That way I have more control over all of this. Then I will set other mesh sizes on other curves. So the curves on the boundaries, as you notice here. And then I just mesh some of these surfaces. I don't mesh all of them. I just meshed the slope surface in the fine volume and all the external surfaces here. Okay. And I'm also using a bias, so I'm even increasing mesh size from top to bottom on the external boundaries. Okay, I'm usually pretty aggressive in this because, as I said, you could really save on the number of elements this way. Okay, the next stage is to bring in the faults, and in this case, let's just do that. Please select it. So this is done. So now I have the fault. So if I go to here now, see I have the two volumes. So if I turn off the volumes, if I select these two, right click, visibility off, you see now I have the meshed fault surfaces inside as well. These don't belong to any volumes. That's why when I turn off the volumes, you could see them. Okay. So I've played up until here. The next stage, which is really the tricky part here, is I'm going to mesh this volume 1 with a TET measure scheme, but I'm going to respect all the triangles that I had in the fault surfaces. So what this does is that it will try to put in all those triangular elements on the fault surfaces and incorporate them directly into the TET mesh of the volume. Okay. Okay, so I've done this. Now I'm going to mesh the volume, and this could take a while because I'm on a very basic laptop here. So as I said, this is my way of making sure that the mesh surfaces of the fault surfaces are explicitly incorporated into the volume mesh of the slope. So this was successful. I don't see any error messages. It's giving me some information about what was going on. And as you notice, the mesh is now complete. So now I have a mesh on the top surface, and it's gradually increasing mesh sizes from around 20 meters to around over 100 meters. Okay, so I've meshed everything right now. And if you click on an element, on a volume on the left-hand side, so on the tree, a model tree, you will see information about mesh. So this is meshed. I have about 187,000 elements on the fine volume. And if I select volume 2, is also meshed, but now I only have around 17,000 or less than 18,000 elements. So really very aggressive. Then I will start adding things to the blocks. Okay, let me just run the whole thing again. So you see I have a lot of stuff down here. So what those does is that I'm just grouping different elements on the nodes on the fault surfaces into groups so that I could more easily select them in Irazu. Generally, in this case, I only need 2 sets of element blocks, one for the fine volume and one for the coarse volume, but I need quite a bit of node sets to be able to set boundary conditions as well as select all the nodes that belong to the fault surfaces, because we need to select those and assign them to discrete fracture networks in Irazu. So what it does is that you notice that it is taking some time. It will try to find all the coincident nodes from the surface meshes of the faults and the equivalent nodes on the TET mesh. And that takes a while because it has to, find all those, search over 250,000 elements and find coincident nodes. Now it's putting all these nodes into node sets, right? So I believe this is done now. So if you look at the left-hand side now, you have blocks. So if I click, block 1, block 2, so these are all the elements that belong to the volumes. And then I have quite a lot of node sets. So node set 1, if you look here, node set 1 is all the fault nodes. So let me see if I can isolate this. No isolate here. So an easier way would be to turn off the volumes here. Okay, so node set 1 is the nodes on all the fault surfaces. So all these nodes are grouped into node set 1. Okay, and then I have individual node sets as well. So let's say node set 4 is just so each individual surface is also put into its own set, just in case I ever need it in post-processing to build the model in Irazu. I typically don't, but there's no harm in putting them inside the mesh, because if you ever do, then you have it here. So node set 2 are all the nodes on the sides. So you could very easily say add all the nodes in surfaces and then give the surface numbers. So let's say here in this case, for example, node set 2 is adding all the nodes in surfaces 10 to 16. So these are these surfaces on the sides. I put them into a node set because they will need to get their own boundary condition type in Irazu. And then node set 3 is all the nodes at the bottom, which again will get their own boundary conditions in Irazu. So once you're happy with this, you go ahead, file, export, and export this as an abacus mesh. Okay. It will export all. It will take a while because it's 250,000 elements. Once the mesh is exported, it will give you some stats about the mesh and how long it took and so on. Then you could head to Irazu and create a new project by importing an abacus mesh. Okay. Let me see where I have this. So import the mesh that you just created. Okay, this could take a couple of seconds here. Okay, please ignore the weird stuff that I have here. I forgot to change my screen resolution, but you can give your project a name. Check all the simulation solvers that you're going to need. So in this case, I need mechanical and hydraulic. I'm going to initialize the model with far field in situ stresses, and I'm going to incorporate discrete fracture networks for the faults. So you select all those options, you save your project. Just to be safe, I always save projects, from the get-go. So this is where you have things in Irazu. So you have, your mesh here, you have some stats about the mesh. So the first order of business is to go and create two materials, one for the fine area, one for the coarse area. And obviously, if you have more blocks, then you add more blocks to the mesh and you add them here. Then you could very easily right click and select the element blocks. So this is the fine volume. So you apply it to fine, and then you select, the coarse, which is element block 2. You could also do it from the top here and apply to coarse. So as you noticed, it's so much easier when you group everything during meshing. Then you could go ahead and create your boundary conditions, the mechanical boundary conditions. So in this case, we need rollers on the sides and pins at the bottom. Okay, so rollers, this will be a roller that allows movement along Z as well as pins. So then you select, I don't know if I can take this up, no. So as I said, you could also select from here or just by right click. So node set 2, I believe, were the nodes on the sides. So you see the nodes on the sides are now isolated for easier viewing. So you could assign them here to rollers. And then you could select node set 2. And as you notice, if the names of your node or element blocks are similar, then Irazu will try to group them for easier processing. So node set 3 are all the nodes at the bottom, and you go ahead and assign pins to them, right? Very easy. It's so much easier than having to, manually select things. If you want to graphically select all the nodes on the side, then you first of all have to be very patient and then ready to make mistakes, right? So it's so much easier to do things during the meshing process. Then you can specify discrete fracture networks. So in this case, let's say you could have either broken or cohesive EFNs. So with the broken, they only show resistance to, the frictional resistance. With cohesive, they will have, cohesive strength, which will be like friction, cohesion, tensile strength, and fracture energies. So if you wanted to, assign all of the faults into a single DFM, you select all of them. And if you notice, they are all selected inside. So you right click and apply it to the DFM. So they're all applied like this inside. That makes it easier. And then you can apply, in situ stresses, go back and, specify for how long you want to run your model and so on, or, specify the kind of, coupling that you want. So in this kind of scenario, you typically start by running, a few mechanical steps, and then you, by few, I mean maybe 50,000 or 100,000. So, and then you add, you either run just hydraulic or hydromechanically coupled, and then you go to mechanical and so on. And, once you're happy with everything, you press the run button to run the simulation. So that's kind of, a very general overview of what I wanted to show. I know we're at the 45 minutes mark here, so I think I'm going to stop here and allow some time for questions and answers.
Great. Omi, thank you so much. That was an excellent, very informative. Thank you. We have one question that's come in so far, and if you have other questions, feel free to add them in the Q&A section. Someone was wondering if they could have access to this geometry in the journal file, the example that you're sharing.
That will be a little tricky. I have to get some permissions. I have permission to show, but I don't have permission to distribute at this point.
Okay.
This was for a project. But, I could probably share more information on how you could do a similar thing in, a more generic file. Okay. Because I have a very similar, I have a cube with a bunch of fault surfaces inside it that shows the same exact process. I could share that for sure.
Okay, great, thank you. let's see, any other questions? We also have some Cubit experts on the line from Coreform that are happy to answer any Cubit questions as well. Okay, here's another one. Have you worked with thermomechanical coupling problems? If so, have you developed any guideline or manual on how to solve the problems in Irazu?
Yes, so we actually have worked on quite a few projects that were thermomechanically coupled, and I believe we have one or two tutorials in our tutorial manual on how to use that module. And there are a few example projects as well as verification projects that are shipped with the software that show you how to use it and how the code was verified.
Great, thank you. So maybe this is a question. So I have Greg Brennan on the line. He's one of our Coreform Cubit experts. Maybe I'll direct this question to Greg. Is it easy for one to develop an interface between Cubit and their own geomechanics software, for example, to read in a mesh into some other third-party solver?
Yeah, and this is probably something that after I answer this, I'll probably have we have Omid answer as well. Cubit offers kind of a variety of different ways that you can develop an interface between it and a geomechanics software or any kind of finite element or simulation software. So one of the ways you can do an interface is through exporting of file formats. And so here, we showed like an abacus input file. But there's, we support Exodus, we support ANSYS, we support LS-DYNA formats. We support open foam formats. We support a lot of different, thank you. We support a lot of different formats here that you can export to. So that's one way to do it. Another way is that Cubit has a built-in Python interface. And so you can actually write Python scripts as well. And then you can call Cubit from a third party or like an external Python engine. So there's a lot of different ways you can interface with that. I guess what I would do is, and that's Omid, how did you guys experience writing this interface or developing this interface for your software?
So from the get-go, we were able to, we incorporated filters for importing abacus. So it was always superbly easy for us. It was just, fine-tuning our import functionality for the specific abacus formats that Cubit was writing, because, the abacus format is not really global. The element types and so on change in the IMP file, but that's a relatively easy change to make. So for us, it's always worked very easily because we could directly import from abacus. And as you mentioned, I generally use the journal file, but if things get a little bit more complex and I need to do things a little bit more programmatically, I will just use Python within Cubit. So you could very easily translate all of your commands that you have here into Python. So it just wraps it around. And then you could use generic Python code as well. So there are cases that I had to, draw something repetitively. So I'll draw it once and then I'll, repeat it with Python.
Okay, and then there's another question from Jay Tong asking whether or not Irazu's operations can be automated through macro-like commands, similar to this journaling in Cubit.
We don't really have any kind of macro capabilities at the moment. We are thinking about, implementing something similar, mostly for, as I showed, for material assignments and so on. There are ways that you could, manipulate, because, once you build something, you could export the run, okay? And the run is written in a JSON format, which is a human readable format. So you could manipulate the run files programmatically, let's say through Python or any other, programming language that you want to use, but Python will be the easiest. In terms of outputs, they are also written in VTK format, so you could open them in ParaView and then extend via scripting, filters, as well as Python.
Great, thanks. Another question I think is asking about Irazu, whether or not Irazu uses MPI parallelization. So you mentioned GPU parallelization.
Yeah, so there's no MPI really. We use CUDA, which is the programming framework language from NVIDIA and their GPUs. So everything is written in C++ and CUDA. We don't really use MPI or OpenMP or anything like that. Those are mostly used for CPU coding. On the CPU side, we just use the CPU to launch the simulation and load it onto the GPU, and also for writing output files. But we don't really do any computations on the GPU, on the CPU. Everything, all the computation is done on the GPU using the CUDA from NVIDIA.
Okay, and then the second part of that question, I'll go ahead and answer, which is about, so if you had a code that did MPI parallelization, partitioning, the kind of domain partitioning in Qubit for a mesh like that, you typically wouldn't have Qubit worry about the MPI parallelization. Usually codes that support MPI parallelization will handle node renumbering and the dynamic partitioning themselves. So that's not really something that you typically would use Qubit for. And we don't support that natively. You might be able to hack something together in Qubit to do that for your code if you wanted to, but that's something that we just typically let the solvers handle. Another question that's come in for Irazu is it possible to model rock structure support interaction in Irazu?
I assume by support you mean like support elements like rock bolts. If so, yes, you explicitly incorporate support elements the same way as you explicitly incorporate discontinuities. So that could be modeled explicitly as well.
Thank you. Great. Well, I think that's all of the open questions that we see. And if there's any other final questions, feel free to ask them. But if we don't see any more, I guess I'd like to thank our speaker Omid today for sharing this webinar with us. This is very eye-opening for me. I always like to see novel applications of meshing, but also just of simulation and how it's applied to the real world. I always think that that's just really really cool. So I'd like to thank you, Omid, for sharing that with us today. I felt I learned a lot.
Yeah, and thank you, Greg, for your expertise as well for answering Qubit questions. As you all leave, if you could answer the survey question that pops up in the web browser, we'd appreciate that for feedback as we push forward. So again, thank you so much, Omid. Thanks everyone for attending, and we'll talk to you all later.
Thanks a lot, Matt, and thanks for the opportunity. If there are any questions, further questions, feel free to reach out to me directly via email. Thanks.
Okay, great. Thank you. Have a great day, everyone.